Hi guys, how you doing? This is chapter 2 on atomic structure, ACE chemistry, and away we go. So we're going to talk about inside the atom and a little bit of history first about how the atom was discovered. So the atom we know is very, very small. It's mostly made up of empty space where the electrons are located, and inside is nucleus where is the neutrons and protons. So you can see the mass is very, 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 very small. 1.67 times 10 to negative 27 kilograms of a hydrogen. That's for hydrogen atom. So inside the atom, quick review. We have the nucleus, which is protons and neutrons, and then electrons that are in the electron cloud or energy levels. So the progression of the atomic theory, starting back to Dalton. Well, before Dalton, there was autonomous, but right now we're just focused on the modern theory. So Dalton, and then it goes into Thomson's plum pudding. We have Rutherford's planetary arrangement, Bohr model, and then with our current model, which is the quantum model, the orbital theory, is what we are going to dive into in chapter 3. So this is Dalton's theory. He basically has developed a structure of a sphere that an atom is indivisible and indestructible. And we know that is false because atoms are made up of small particles, neutrons, protons, electrons. Atoms of the same element are exactly alike, which is true. Hydrogen is the same as hydrogen. Atoms of different elements are different, which is also true. And then compounds are formed by joining of atoms of two or more elements, which we know is true as well, which makes sense. So the structure of an atom, there's a series of experiments in the late 1800s and early 1900s. This is basically the golden age of the atomic theory, where all these different scientists were studying the structure. In 1897, a cathode ray tube by J.J. Thomson was his go-to apparatus. And basically it was charged particles that were moved, you can see here, from a positive plate to a negative plate. So the charge he knew was an electron because it was being bended towards the positive and deflected by the negative. So what's so important about his experiment is that we knew that there was charged particles within atoms, and specifically the electron. So you can see here we have positive and negative fields, and we shoot a positive particle through, it will deflect towards the negative, and a negative will deflect towards or go towards the positive, and the neutron, which is neutral, will just go right through the straight because it's not going to be affected by any magnetic field. So checkup number 1. So a beam of electrons is passing closely at highly negative charged plate. When the electrons pass close to the plate, they are deflected away from the plate. So what deflection would you expect, if any, when the experiment is repeated with beams of protons and beams of neutrons? And which subatomic particle would be deviated the most, meaning the most deflection, and why? So would it be the proton, the electron, or the neutron that gets deviate the most, and then why? Ernest Rutherford, he was next up, 1920. He had the gold foil experiment. Basically, the gold foil shot alpha particles through gold foil, and majority of them just went right through, which is what he expected. But what was not expected was deflection of these alpha particles. So why is it so important? Information about the structure that he found was that in an atom is mostly empty space because they all basically went through, but those certain deflections that shot right through and right back showed that there was a center of an atom that's very, very dense. So he called that the nucleus. So you can see here that his plum pudding model, the one that J.J. Thomson dubbed, this is what he expected, but what he happened to see is that most of them went through, but there were some deflections. So he basically discovered that the nucleus was the center of an atom. So Rutherford came up with his model, which is the the planetary model. Say that electrons orbited the nucleus like a sun, or like planets orbiting the sun, and he created that the charged particle inside were protons, in the nucleus where electrons were orbiting. Bohr model, which is very common of what people thought what we expect to today, is that he discovered energy levels. These energy levels is where electrons are located, and as you get more and more protons and neutrons, you get more electrons, which grow into more energy levels. How he figured it out was basically how light was being emitted when electrons got excited. So the reason why we have fireworks and whatnot, we have photons that release when electrons go down in energy level. So electrons get excited, and then they fall back down, and that energy they release is in the form of light. And the distance they travel is different lights. So you get reds, different wavelength of reds and blues and whatnot, depending on how the electron transfers down into energy levels. So that's kind of cool. Now, what we have is building upon Bohr model, the quantum model, and this is where it gets a little more hairy and a lot more abstract. So yes, there are energy levels, but within those energy levels, there are actually these orbitals. And I think of them as rooms within the classroom or the house. So you have electrons are in different parts of the room of the house, and the house is the whole electron cloud. And then as you have more energy levels, you have more and more houses. So you can see here by Schrodinger, yes, the same guy for Schrodinger's cat. You can see here that these are these lobes here are where the electrons are located, and the nucleus is still in the center. But then you have this big orbital in the center, and then these small ones a little further out, and then you have a big one, and then you have more of these lobes around. So it can get very complicated, but it makes the most sense. So, first thing we haven't talked about yet, or the atomic particle we haven't talked about yet, is a neutron. It's the last one to get discovered. Why is that? Because it's neutral. 1932, Chadwick discovered it, basically using, again, some foil, beryllium foil, and it shot out and broke apart the beryllium atom. And then in nitrogen gas, nitrogen was used because it's inert, would basically detect a movement, and these movements weren't positive or negative, so it helped determine that there was some extra mass in there of a neutron that kept it stable. So we have Chadwick in here. 1932, he discovered the third subatomic particle, the neutron, which called it neutron because it was neutral, and it resides in the nucleus where the protons are also located. So quick review of the experiments. Protons are positive charge. Their relative mass, so that mass compared to other things in the atom, is 1. The symbol is P, or P+. Neutron is 0. Its mass is also the same as proton, and its symbol is N, or N naught, or N0. Electrons -1 charge, its mass is relatively negligible, meaning it doesn't have any mass effect on the atom. and then the symbol is E negative. So section 2.3, the nucleus. So a few things you need to talk about is symbols. So a proton, or the Z number, is the number of protons, the atomic number, and the number of electrons if it's neutral. So you look on the periodic table, you look at carbon. Carbon is number 6, so it has 6 protons. And if it's neutral, it has 6 electrons. The atomic number is how the periodic table is made up, organized. Now, if the proton changes, the element changes. So you have to make sure you never change. If you're talking about carbon, it has to have 6 protons. If you're talking about neutron or nitrogen, it has to have 7 protons. Isotopes are how symbols are written. You have the symbol element in the middle, X. The A number is the mass. So that's both protons and neutrons. Again, electrons aren't calculated. And the Z number, which is the number of protons. Sometimes the Z number is left out, because if you know the element, you know the Z number, or the atomic number. Okay, so simple subtraction can figure out the number of neutrons between A and Z. If you know the protons, you know the mass, you can figure out the neutrons. So quick review here, let's go. Determine the number of electrons, neutrons of these neutral atoms. So we have vanadium. It's neutral, so we know it has 23 electrons because it has 23 protons. And then you simply subtract 23 and 51, and you get 28 neutrons. You can pause this and try the other ones. We got strontium 38 or 84 and phosphorus 31. But these are your checkpoints. Electrons should be 38, and then neutrons should be 46. And then for phosphorus, 15 electrons and 16 neutrons, because 16 plus 15 is 31. All right, isotopes. Isotopes are the reason we have decimals in the periodic table of masses. It's the same number of protons because, again, protons change. You change the element, so you can't change the element of isotopes. But the only thing changes is the neutrons because they have different masses. So boron 11, or boron written as 11 over 5. Those are two ways to write it. Hydrogen has three different isotopes. You have hydrogen 1, hydrogen 2, hydrogen 3, or tritium and deuterium. So you can see the neutrons are changing from 0 to 1 to 2. Helium has two basic isotopes, helium-3 and helium-4. You can see helium-3 has 1 neutron, where helium-4 has 2 neutrons. And you can see lithium also has a couple isotopes. They all have 3 protons, but the number of neutrons change. How many protons, neutrons, electrons? All right, so neutral atom has the same number of protons, same number of electrons, and the mass can be found by looking at the number of protons and neutrons. Now, what happens if you do gain or lose electrons? You become charged. You become positive or negative, a cation, or a negative, an anion. So metals generally going to lose electrons. So you can see sodium here has 11 electrons. It loses 1, and now it has 10 electrons, so it becomes a +1 charge. Where chlorine over here has 7 in the outer electron, 8 and 2, that gives you 17 electrons. You add 1 more, goes from 7 to 8, become a -1 charge because it gains a negative electron. All right, so you can see here the math involved with chlorine going to chlorine -1. Chlorine has 17 protons, has 17 electrons, being neutral. But if it gains an electron, it goes from 17 to 18. So you can see if you do the math of 18 negatives and 17 positives, it will become a -1 charge. Same idea for magnesium. Magnesium has 12 protons. Again, neutral means 12 electrons. And then it's going to lose 2 electrons. So that means if you have 12 positives, 10 negatives, you become a +2 charge. All right, last slide is basically just practice. Determine the number of electrons for each of these atoms, or ions, sorry. We got potassium +1, nitrogen -3, oxygen -2, and gallium +3. So you can try these out, pause the video, and then we're going to come back and check the answers. All right, so hopefully you can start back up. We got 18 electrons for potassium, 10 for nitrogen, -3. Oxygen has 10 because 8 has started with 8 and it gains 2 electrons, and gallium should be 28 because it's +3. So 31 protons, 31 electrons, then a +3 will go from 31 to 28. So you can see that if it's positive, the electrons go down, and if it's a negative charge, electrons go up, which makes sense. All right, hope chapter 2 is done. We'll have a few more practices, but pretty simple stuff, and then we'll move on to chapter 3.